Hi and welcome to day 5 of complex numbers. This is the 5th and final video of this unit. Alright, so for the opening exercises, write each of the following quadratic expression as a product of linear factors. Verify that the factored form is equivalent. So for the first one, I'm looking for factors of 27 that add up to 12. So my factors of 27 that add up to 12 are 3 and 9. So it would be x plus 3 and x plus 9. And to verify, I would just multiply it out. Use the box method if you want. So x and 3, x and 9, x squared, 3x, 9x, and 27. So it's x squared plus 12x plus 27. Looks good. So x squared minus 16. That's a difference of two perfect squares. So that's x plus 4, x minus 4. And again, when I multiply it all out, we'll have x squared 4x, negative 4x, and negative 16. So those will cancel out. So it's x squared minus 16. X squared plus 16 is going to be x plus 4i and x minus 4i. Use the box method again. X 4i, x minus 4i, x squared 4xi, negative 4xi, and then this would be negative 16i squared, and I squared is negative 1, so negative 1 times negative 16 is plus 16, and then those two are going to cancel each other out, so we have x squared plus 16. So then for the last one here, it is not factorable because there are not factors of 5 that add up to 4. So I'm actually going to have to use the quadratic formula to help me factor. So A is 1, B is 4, and C is 5. So x equals negative b, so negative 4 plus or minus the square root of b squared is 16 minus 4 times 1 times 5 all over 2 times 1. So x equals negative 4 plus or minus the square root of 16 minus 20 over 2. So x equals negative 4 plus or minus the square root of negative 4 over 2. So we'll have x equals negative 4 plus or minus 2i over 2, and that simplifies to excuse me, negative 2 plus or minus I. So to actually write that in factored form, that would be looking at each individual root. X equals negative 2 plus I, and x equals negative 2 minus I. So I'd have x plus 2 minus I equals 0, and then x equals plus 2 plus I equals 0. So all I did was set each of those to 0 and solve them. So my one factor is x plus 2 minus I, and x plus 2 plus I. And I don't really have to verify that since we just used the quadratic formula to find it. To me, that's good enough for verifying. All right, on to the next one. So example 1. Consider the polynomial p of x equals x cubed plus 3x squared plus 5 minus, or plus x minus 5, whose graph is shown on to the right. Look at the graph. How do we know that there is only one real solution? Well, it only crosses the x-axis once. Is it possible for a cubic polynomial function to have no zeros? No, because of n behaviors in opposite directions. All odd-powered polynomial functions must cross the x-axis at least once. Well, it must be at least once. From the graph, what appears to be one solution of the equation? Well, looking at the graph, it looks like x equals 1 is a solution. How can we verify that it's a solution? We can sub in 1 for x and see if it equals 0. So, according to the remainder theorem, which is what I just described in part D, what is the one factor of the cubic expression? Well, if x equals 1 is my root, then x minus 1 is my factor, or solution. Factor out the expression you found in part E from that. Actually, I want to go back up real quick. We should actually probably show this in part C. 9, it was called P of that. So P of 1 equals 1 cubed plus 3 times 2, or 1, excuse me, squared plus 1 minus 5. So that would be P of 1 equals 1 plus 3 plus 1 minus 5. So P of 1 equals 0. Just to verify that. Factor out the expression you found. You have two choices. You can use reverse target or you can use long division. So I'm just going to do long division real quick. So my first one is going to be x squared. And then I'm going to subtract, change all my signs. And then I'd have 4x squared, bring down my plus x. X times what equals 4x squared? Well, that would be 4x. So when I multiply out 4x squared minus 4x, and then I'm going to subtract, so change everything to its opposite. So those cancel out. And then I will have a 5x and bring down my minus 5. So that would be plus 5. So 5x minus 5 when I multiply, and then when I go to subtract, this is good. Oh, hang on. Go to subtract, everything's going to change to its opposite, so I get 0. So that means we have x minus 1 and x squared plus 4x plus 5 as my factors. So let's see where we get. What are all the solutions? So we had x minus 1 as a factor, and we also had this x squared plus 4x plus 5. Now, if you remember, this was in one of the opening exercises, and instead of redoing all that work with the coordinate formula, I'm just going to write out the factors. So it would be x plus 2 plus I, and x plus, or sorry, x, not plus, it should be x minus 2 plus I, and x minus 2 minus I. So that means my solutions, so set them equal to 0. My bad for not setting it equal to 0 here. So that means that x equals 1 is a solution, and x equals 2 minus I, and x equals 2 plus I are all my solutions. So write the expression in terms of linear factors, which is essentially what I just did right here. So x minus 1, x minus 2 plus I, and x minus 2 minus I equals 0. Ooh, nope, no equals 0, because it says an expression. Alright, let's look here. Write each polynomial in terms of linear factors. The graph of y equals x cubed minus 3x squared plus 4x minus 12 is provided for exercise 2. So that's over there. So for the first factor, x, and I have x times x squared plus 5. Well, we look at the factor, this is really going to be x plus I radical 5 and x minus I radical 5. And then for number 2, it looks like you'd be able to do factor by grouping, so let's try and see if that works. And we have an x squared in common with x minus 3. And then here we have plus 4 and an x minus 3. So we have x minus 3 times x squared plus 4. So it's x minus 3 and x plus 2I and x minus 2I. And then we can just use the graph over here to verify that x3 is a root, therefore x minus 3 has to be a factor. Alright, example 2. Consider the polynomial function p of x equals x to the fourth minus 3x squared plus 6x squared, or 3x cubed plus 6x squared minus 12x plus 8, whose corresponding graph is y equals that same function, as shown to the right. How many zeros does p have? Part 1 of the fundamental theorem of algebra says that this equation will have at least one solution in the complex numbers. How does this align with what we can see from the graph at the right? Well, we know we should have 2 real solutions, and we have 4 possible answers. Therefore, we should have 2 complex and 2 real. So what I want to say here is, since the part 2 exercise, there appear to be two zeros. Okay. Identify 1, 0 from the graph. Well, x equals 1, or you could have said x equals 2. Either one works. Use the polynomial division to factor out one linear term from the expression. Okay, so let's see here. I'm just going to do x minus 1. Let's do reverse tabular method. So this is x to the 4th negative 3x cubed x squared x, and I think I need to do one more. And then this would be, so it would be 6x squared negative 12x, and then 8. And here we'd have x, and then minus 1. So we know that this must be x cubed, because x cubed times what equals x to the 4th. Sorry, this has to be x to the 4th, so that means this is x cubed. I'm writing it in the wrong spot. Oh no, don't do that. So that's x to the 3rd up there. So that means this is negative x cubed. So that means this has to be negative 2x cubed. Make it a negative 3x cubed. So that means I'd have to have a negative 2x squared. And then that would make this a positive 2x squared. And I need that to add up to 6x squared, so that makes this 4x squared. And x times what gives me 4x squared? It'd be 4x. So 4x times negative 1 is negative 4x. This needs to be negative 12, which just means this needs to be negative 8x. And x times what would give me negative 8x is negative 8. Negative 8 times negative 1 is positive 8, which works. So I'd get x cubed minus 2x squared plus 4x minus 8. So after I divided out one of my linear terms, which was x minus 1. Ooh. Now we have a cubic polynomial to factor. We know by part 1 of the fundamental theorem of algebra that a polynomial function will have at least one real zero. What is the 0 in this case? Well, the other 0 we had was 2, so that should also work. So x equals 2 should be the other one. Use polynomial division to factor out another linear term. So I'm going to work with the function that I just had. I'm going to take my answer here, which was x squared or cubed minus 2x squared plus actually no, I'm going back to the original. So x minus 2, this time I'll do long division, x to the 4th minus 3x cubed plus 6x squared minus 12x plus 8. Alright, I'm full of indecision tonight. I'm going back to my original plan. It's going to take too long if I do it the other way. X minus 2, and we'll do long division with x cubed minus 2x squared plus 4x minus 8. Okay, so I have x squared equals x cubed minus 2x squared. And I'm going to go ahead and subtract that, change everything to opposite, so they both cancel out. So then I bring down my 4x minus 8 and plus, I have no zero x's that I'm going to do, so plus 4, because x times what gives me 4 x's? 4, so 4 times x is 4x. 4 times negative 2 is negative 8. So go to subtract, change everything to the opposite, you get 0. So far we have x minus 1, x minus 2, and now x squared plus 4. And it says, are we done? The answer is no, we're not done. We have our x minus 1, x minus 2, and our x squared plus 4. Well, x squared plus 4 can be broken down one more time to x plus 2i and x minus 2i. Now that the polynomial is in factored form, we can quickly see how many solutions there are to the original equation. So we have 2 real solutions. Sorry, there's 4 solutions. Two real and 2 complex. And what if we had started with a polynomial function of degree 8? Well, same process. Find 1, 0, divide, find another, divide, and so on. So divide and so on. Alright, that's it. That's the last video for this unit and for a while probably. Let's see.